Hi everyone, today we do Cambridge A-Level Further Maths, syllabus code 9231, and for paper pure further pure 2, this is the variant 3 from the Major 2025 series. We go for question 4 today. The previous questions are already done. Second order differential equation, which is not homogeneous, there is a function on the right hand side is not equal to 0. And they are also given us some boundary conditions when t is 0 and dx dt is also 0. So they want us to find the particular solution of this differential equation. So let's start by first, recall for the solution of the second order non-homogeneous differential equation. The solution is given by the form x of t is the sum of the homogeneous solution and the particular solution. So this one will be the sum, which is the what we call the superposition principle. So we have to find each of these homogeneous and particular parts. Okay, so for the homogeneous part first, let's do the homogeneous part first. So we set the second order differential equation to be equal to 0, and that's how we find the homogeneous part. So obviously in this form you can recall that what we do here is we assume a homogeneous solution in the form of an exponential function. So maybe e lambda t. So we know that dx dt will be lambda e lambda t, and the second derivative will be lambda square e lambda t. And we can use this, we substitute this back into the differential equation. And from here we can factor out the exponential terms, and we are left with an quadratic equation in terms of lambda, right? This is called our auxiliary equation. So obviously we know that the exponential function will tend to 0, but it will never equals to 0. It will never actually equals 0, so that one will not yield any solutions for us. Only the auxiliary equation, it will give us some answers, so we can factorize it to become this one. So use us to be lambda, this will be equals to 0, right? It's equals to 0, so lambda equals to -2 and lambda equals to 1. So be lambda 1, lambda 2. And since the roots of the auxiliary equations are real, so then the what we call the homogeneous solution will take the form of a arbitrary constant with lambda 1 t together with another arbitrary constant with another lambda 2 t. Okay, so this is the form of the solution for real roots from the auxiliary equation, and we just substitute the values of lambda into the solution. So just like that. Okay, so that's for the homogeneous part. Now for the non-homogeneous part, we have to use the method of undetermined coefficients. Undetermined. So again, we assume a solution in the form of dependent on what the right hand side of the function or the non-homogeneous part of the function will look like. So if it's in the case of a sine function, we're gonna have to assume a constant multiplied by sine and the cosine. In the form of a polynomial, we assume a polynomial with the same order, in this case order of 2, and assign them some constants also. And yeah, I think we just, in this case, is a polynomial, so we assume a solution of the particular form in the form of what constants can we use here? We use lambda, c is taken, so we use we use c3 t squared c4 t plus c5. Okay, so we're using some arbitrary constants, and from this we have to find, we find the first derivative and the second derivative So yeah, this is our first and second derivative, and we have to substitute back into our original equation, or differential equation, and equate it to the polynomial. We have the second derivative, add the first derivative, adding or subtracting 2 multiplied by the original function of x. And this is equals to 2t squared plus t minus 1. And what we do here is we're not solving, we're just comparing both sides so that we can compare the coefficients of the respective polynomial terms. So for t squared, we compare with t squared. So we can try to expand this a bit first. Okay, so hopefully you should be able to see that we can equate or not equate, but compare the coefficients of the terms here. T squared, for the t squared coefficient, we can compare 2c3 equals to 2. So c3 will be equals to negative 1. For the t coefficient, we know 2c3 minus 2c4 on the left hand side equals to 1 on the right hand side. So we also know c3 is negative 1. We can just substitute that into the equation. So we have c4 equals to negative 3 over 2. Now finally, for the constant term, we have all three constants involved on the left hand side, and equals to negative 1 on the right hand side. So c5, after substituting c3 and c4, you should be able to get negative 5 over 4. And so that leaves us with our particular integral. That leaves us c3 negative t squared minus 3 over 2t minus 5 over 4. Okay, so this is our particular integral. And therefore, our general solution of x, we just have to add this one with the homogeneous solution. So we have c1e negative 2t, c2t minus this particular solution. Okay, but we're not finished yet, because we want to find not just the general solution. We need to solve also for these two arbitrary constants, which given the boundary conditions we can easily do. So boundary conditions, I will write that first. T equals 0, x equals to dx dt equals to 0 also. Okay, so let's deal with the x equals to 0 case. So we know x 0 equals to 0, and that means all the exponential terms goes to 0, as well as all the the terms of the polynomial with t. So we can reduce it to c1, c2 equals to 5 over 4. Okay, so that's the first equation. We have two unknowns, so we cannot directly solve for this. We need the second equation that's coming from the dx dt. So dx dt, we have to differentiate. So differentiate it carefully. Okay, we have so this is dx dt, and now we substitute the values of x equals to 0. Sorry, not x equals to 0, t equals to 0, right? T equals to 0. So all the exponential terms reduce to 1, and we're left with this. Okay, so this is the first equation and the second equation. Solving simultaneously, if you either you use your simultaneous equation or your calculator to solve, should be able to get c1 is negative 1 over 12, and c2 is 4 over 3. And therefore, okay, the final particular solution with all the constants specified, xt equals to negative 1 over 12 e negative 2t plus 4 over 3 e t squared 3 over 2t minus 5 over 4. Yeah, this is the final solution. So second order differential equations, this describes a lot of systems in nature, a lot of oscillatory systems such as, I don't know, spring mass damper. But yeah, this is an important knowledge to know if you're going further into mathematics, physics, or engineering. Yeah, so this is second order differential equations. Thanks for watching.